Hello everyone. We have been working on a data driven approach to help businesses make smarter capacity investment decisions under demand uncertainty. By simulating different demand scenarios, we identify investment strategies that stay stable across changing conditions. This helps minimize risks like overinvestment or shortages and replaces guesswork with a more structured, scalable decision making process. This work is a part of my poster presentation at Informs Analytics Plus 2025 conference, which is taking place this month. It is my pleasure to present my work on the sensitivity analysis of mixed integer linear programming based capacity expansion decisions under demand uncertainty. This work is guided by my advisor, Dr. Ignacio Grossman, and is being conducted in collaboration with Johnson & Johnson's digital supply team. Taking the example of supply of crucial surgical instruments, Johnson & Johnson need to know how do they allocate their resources efficiently to plan their capacity investments today to meet the demand 2 to 3 years later because of the long lead time. The demand isn't constant though. New product launches and other factors create uncertainty. To tackle this, we propose a three-step approach. First, generating demand scenarios using Monte Carlo simulations by incorporating real market conditions and other inputs. Next, feeding these scenarios one by one into our optimization model, the MILP model, to maximize the demand fulfillment and minimize the unnecessary production and investment costs. Even with a solid optimization model, we need to understand how changes in demand impact the decision making variables. Therefore, we perform sensitivity analysis and to understand how investment decisions should impact and should be adapted to the changing demand, we use parametric MILP approach. This method systematically explores how solutions change as demand varies. It works by identifying distinct regions in the parametric space called critical regions where the optimal basis remains unchanged. Using this iterative algorithm, we determine these regions based on the optimal basis. In our case, the problem identified 3 regions, each corresponding to a unique strategy. A combinatorial approach helps us visualize these transitions, pinpointing where the investment plans could shift. This allows us to map out the transition points, understand the effect of demand fluctuations, and derive the best investment and production strategies without running repeated optimizations. So, I'll not be going over the details of this algorithm. But we tested a small problem with this algorithm with 1 product, 3 work centers, and 4 time periods under an uncertainty range covering 80 to 120% of the nominal demand. This gave us key investment strategies along with the optimal expansion plans. But this is the beginning. Future work will focus on scaling this to business-based models with broader uncertainty ranges, perhaps also utilizing some existing tools and making this decision-making process even robust. Now let's visualize these insights using my interactive dashboard. I'm hosting my dashboard locally and it's up. Welcome to our capacity management planning dashboard. By now you have an idea of how we approach demand uncertainty. This dashboard allows you to build your own supply chain network by uploading the data sets, defining the demand uncertainty. You can then visualize demand distributions, critical regions, and obtain insights into investment plans, production strategies, everything all in one place. Let's get started. First, to build the network, you need to upload your data sets in a specific format. I'll go ahead and upload mine for my test problem. If you're using this tool, you can download sample files to see the required structure and input details, work centers, products, and demand data sets. Next, you set the demand uncertainty. I'm choosing 80 to 120%. Uniform probability distribution, which is simplest For my supply chain model, I'll go with combinatorial algorithm and discrete space search approach. Clicking solve. If you need more details, there's an expander section here explaining these choices. You can explore different methods. Now, the model is solved. First, we visualize our demand distribution across different time periods. Each scenario is categorized as minimum, nominal, and maximum demand. Next, we see the cost function variability across the critical regions. These arise from the piecewise linear MILP solutions. Now, the key part, capacity investment strategies. The dashboard displays definition of optimal investment plans along with their probability of occurrence in this pie chart. Another key decision variable is production levels. These helps strategize decisions in greater detail to meet demand peaks. The stacked production levels give an overall estimate. Next section acts as your personal investor planner, which helps you analyze the sensitivity even better. You can select demand values as you anticipate. Say if demand is in the mid to lower range in the first 2 periods and in the mid to higher range in the third and fourth periods, the model suggests the best investment plans accordingly. It might take a moment, but this is where you can experiment with different scenarios and see which investment plan suits you better. For example, the optimizer suggests going for plan E mostly and maybe also plan B. Finally, you can download the solution file for further analysis, including inventory levels and other metrics. That was a quick walkthrough of the tool. Please feel free to reach out if you have any questions. Thank you for your time.